as we get started today, I want to take a look at your homework from last night. You did page 35, numbers 14 to 36, the even. We're going to first, though, review over some terms real quick, and then we'll take a look at the homework, and specifically interested to see on 26 to 36 who the best guessers were. And we'll see how we did there. All right, so before we get into the homework, I want to quickly review some terminology. We said that when we put an angle on the Cartesian plane, we need to remember that every angle, of course, has two sides. The beginning side of an angle, class, is referred to as the initial side. And then the angle will rotate until it gets to the ending side called the terminal side. If the terminal side ends up in, say, quadrant 3, then we could call the angle a quadrant 3 angle. Okay, if it ends up in quadrant 1, quadrant 1 angle. Right now, does quadrant 3 angle necessarily mean that the angle is a reflex angle? No, because there's two directions of rotation, right? If an angle rotates clockwise, class, we refer to it as a negative angle. But if the angle rotates counterclockwise, then it's a positive angle. So it's possible for an angle to wind up in quadrant 3 without actually being a reflex angle. It could be a negative obtuse angle that winds up there in quadrant 3. Now, we said it is also possible that an angle's terminal side may not wind up in a quadrant at all. Which angles wouldn't end up in a quadrant at all, class? 90 degrees, 180, 270, 360, and so on and so forth, right? If you just keep going around and around and around, we would call those angles, Ethan, quadrantals. Good. And that assumes, by the way, that the angles are in standard position. What does standard position mean, Jamie?
The vertex is at the origin.
Good, vertex at the origin, and that the initial side is where?
On the x-axis.
Specifically, which side of the x-axis?
The positive side.
The positive side of the x-axis. Good. Vertex at the origin and initial side on the positive x-axis. We did say that angles can share an ending side. For instance, think about that reflex quadrant 3 angle, or the same terminal location but a negative obtuse angle ending in quadrant 3. Well, if their ending side is the same, we'd refer to those angles, class, as being coterminal angles. And to find coterminal angles, Quentin, what do we have to do?
Find the degree of one angle and subtract 360.
Or add 360 or subtract 360, right? Either add or subtract 360, and you could add 360 multiple times, or subtract 360 multiple times to get those coterminal angles. Looking at the homework, page 35, numbers 14 to 36, the even, they gave you, first of all, a 60-degree angle. They wanted you to find 3 coterminal angles. All the coterminal angles between negative 720 and 720. What were your 3 coterminal angles on number 14, Ethan?
420 degrees, negative 300 degrees, negative 660 degrees.
Good, 420 degrees, negative 300 degrees, and negative 660 degrees. Number 16, what were your coterminal angles? Those angles coterminal with a 225-degree angle. Jamie?
585 degrees, negative 135 degrees, and negative 495 degrees.
Good, 585 degrees, negative 135 degrees, and negative 495 degrees. Number 18, they give you a negative 315-degree angle, looking for the 3 coterminal angles within 2 revolutions either way. Quentin?
405 degrees, 45 degrees, and negative 675 degrees.
Good, there's only one negative coterminal angle that falls within 2 revolutions because I've already started with the first negative, so negative 675 degrees, and then positive 45 degrees and positive 405 degrees. Number 20, coterminal with negative 45 degrees, Ethan.
315 degrees, 675 degrees, and negative 405 degrees.
Yeah, those numbers look awfully familiar, don't they? 315 degrees, 675 degrees, and negative 405 degrees. Number 22, they give you a negative 410-degree angle. Well, you can't subtract 360. That would give you negative 770. That falls beyond the second revolution negatively. So we end up adding 360 3 times. And you could use that K function on your calculator, or you just do plus 360 plus 360 and do it that way. And what did you get for your answers, Jamie?
Negative 50, positive 310, positive 670.
Degrees in each case, right? Negative 50 degrees, positive 310 degrees, and positive 670 degrees. And then for number 24, your three coterminal angles, Quentin.
690 degrees, negative 30 degrees, negative 390 degrees.
Excellent. 690 degrees, negative 30 degrees, negative 390 degrees. We should feel really comfortable with coterminal angles by now. Adding, subtracting 360 should not be a challenge for us. So let's take a look at the part you're actually looking forward to going over, and that's numbers 26 to 36, the even. You were supposed to identify what size angle you thought this thing was. So the first angle they give us is goes through the point 1, 4. So on your graph paper, should apply to the point 1, 4. Drawn a line back to the origin so that this is my angle, and given an estimate of how big you thought the angle was. Quentin, what was, actually let me go ahead and put your, all right, so Quentin, what was your guess on number 26?
87 degrees, negative 273 degrees.
Sorry, say that one more time.
87 degrees, negative 273 degrees.
All right, hey, I like you deviated from the multiples of 5 and went with a more randomized number there. Jamie?
I had 75 degrees, negative 285.
And Ethan?
80 degrees, negative 280.
All right, and it is actually 76 degrees with a negative 284 degree angle. So Jamie within a single degree. Good guess, Jamie, with the first point. Let's go to the next one. And number 28, the point was negative 7, 2, so negative 7, and then up 2, and connecting here. So we're looking at that angle this time. And let's start with Jamie, since you got the last one.
Positive 170 degrees and negative 109 degrees.
170 and negative 190. All right, Ethan?
160 degrees and negative 200.
And that's Ethan's guess. All right, and Quentin, your guess.
165, negative 195.
165, negative 195, and it is 164 degrees. So almost gave Ethan the point. Quentin with the point there. All right, let's see on number 30. Let me draw a new graph grid here. We had 2, negative 6. So positive 2, downward 6. And so we're looking at this reflex angle. And it might have been easier to think of the negative angle and then add 360 to get the positive angle here. I don't know. Let's see here. Quentin, what did you have?
285, negative 75.
285 and negative 75. All right, Jamie?
295, negative 65.
And Ethan?
280 and negative 80.
280, negative 80. And this angle is 288 degrees, which is closer to Quentin's answer. So Quentin with another point. All right, next one, and this is one that we may have a tie. I'm curious. The point was negative 3, negative 3. All right, so move the camera here in just a minute. So negative 3, negative 3. So looking at this angle here. And I'll drag the camera over here to get that whole chalkboard again. Let's start with Jamie. What'd you have?
225 degrees, negative 135 degrees.
All right, Ethan, what'd you have?
I think I guessed it.
Number 32?
Yeah, I think I went from 30 to 34.
Oh, that's a shame. Quentin?
225, negative 135.
All right, both of you had the exact same guess. And on the surface, I'd say, that's not suspicious. But think about it. To go over 3, down 3 is a perfect bisector of the 90. It's got to have a 45 degree angle here. 180 and 45 gives us exactly 225, and both of you got it exactly right. And Ethan could have been on the board with a point here had he just done it, because I know he would have thought of that. All right, number 34, a much more challenging one, where we have 3/4, negative 4. So 3/4. And then negative 1, 2, 3, 4, so something like this. And quite the reflex angle here. And let's start with Ethan.
Negative 80, well, 280 and negative 80.
280 and negative 80. All right, Jamie?
I also had 2.
Also 280 and negative 80. All right. Quentin?
273, negative 87.
Negative 273 and negative 87. and it is exactly 281 degrees. So points for Jamie and Ethan. And that makes it interesting coming into the last one, because -2, 0. Well, -2, 0 lies here, so we're looking for this angle. And Quentin, what did you have?
180, -180.
What did you have, Jamie?
A 180, -180.
How about you, Ethan?
Quadrant. I searched for 180 and -180.
There it is. It is 180, -180. All of you had it. Unfortunately, that means we have a tie. So you and Jamie can split the... I'm just kidding. We'll give you each one.
Yeah.
Say split the bite size, Three Musketeers. All right, good job on those there. All right, next section in your notes. Hopefully that was fun, and I don't know, a bit of a break from the more rigid routine mathematics. You know, actually doing guesses. You know, how often does that work? Oh, I promised to show you how to learn the actual value, didn't I?
Yes.
Yes. Okay. I should do that then. All right. So let's take number 28. Get your calculators out real quick, and then we'll get to the next section of notes. Number 28 gave you the point -7, 2. So we're backward 7, and then we're upward 2 to this point here. And the question is, how big is this angle? Well, what I do is I just draw a little line to the axis to form a little triangle, which has a side of 7 and a side of 2. And I can use what trig function to find this little theta, class?
Opposite or adjacent.
Which would be
Tangent.
tangent. So I said, well, the arc tangent then of theta is going to be opposite 2 over adjacent 7. Do that on your calculator. Take the arc tangent of 2/7, and what do you get?
0.0.
Arc tangent of 2/7. 16 degrees, right? Well, if this is 16 degrees, I know that total there's a 180 here, right? So I just take the 16 off, and it gives me everything else, which is the 164. So that's the way you can actually figure the exact values of these. And so that's how I got the final answers.
Found that out.
Yeah, but I have to tell you that afterwards, because otherwise it ruins the fun. And really, frankly, if you had to go through and do arc tangent on every one of them, is that fun? No. Now, winning is fun, right? But, so, I mean, if you'd figured it out on your own, right? Because the only rule was you couldn't use a protractor. I didn't say you couldn't use a calculator, so no protractor. But, you know, anyway. All right. Now, next section in your notes. I mentioned to you in a previous lesson that it's important that when you write, for instance, like we just did, 164 degrees, that we actually do write degrees. Because without a degree symbol, an angle measurement is assumed to be a whole different unit. Next section of your notes, another unit to measure angles, and this we call this radians. 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 Okay, a radian is another unit to measure angles. So just as we could measure angles in degrees, we can measure angles in radians. Here's your definition for 1 radian. 1 radian is equal to the central angle of a circle. 1 radian is equal to the central angle of a circle. 1 radian is equal to the central angle of a circle for which the intercepted arc equals 1 radius. 1 radian is equal to the central angle of a circle for which the intercepted arc equals 1 radius. Now I want to take you back just a little bit to geometry last year. And I showed you an interesting kind of construction thing. I had you draw on your papers a circle, okay? And then I had you mark any point on the circle. And with your compass, you were supposed to measure off that radius distance. And then from that point, measure off radius distance. 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 And it should work that when you get back here, I'm a little off because my compass slid just a little, it should hit the same point again. And the thought is this, that from the center, this is a radius here, radius here, radius here. I get a little,
Triangle.
not just a triangle, an
Equilateral.
equilateral triangle, don't I? And then another equilateral triangle, and then another equilateral triangle, and another equilateral triangle, and another equilateral triangle, and another equilateral triangle. And in fact, if you look around the outside, it's a hexagon. A regular hexagon, right? Equilateral and equiangular. So the thought is this, how big is this angle right here, class?
60 degrees.
60 degrees, right? And so is this, and so is this, and so is this, and so is this, and so is this. And we get exactly how many 60s as we go around. 6 of them, right? So the 6 equilateral triangles fit together to make a complete revolution, right? Or along the arc, a complete circle. Well, you understand that this chord is equal to the radius. How does the length of the arc compare to the length of the chord?
They're equal.
They're not equal.
They're not equal.
Between 2 points, the shortest distance is always a straight line. So how does this length compare to this one? The arc is longer than a radius. Does that make sense? So if you were a little ant and you were on my chalkboard, the quickest way to go from this point to this point would be to walk along the white chalk line, not along the blue chalk arc, correct? So imagine then, if I measured the arc equal to the radius, it might be something like that. Just a little bit shorter, right? So if I were to make the angle, it would be something like that. Now the arc is equal to the radius instead of the chord equal to the radius. Does that make sense? So what's interesting then is it would take, notice it takes exactly 6 60s to get around, right? Well, if this right here is 1 radian, the measure of a central angle of a circle for which the intercepted arc is equal to a radius, since this is a little smaller, you realize it's going to take about 6 of these radians to go all the way around, right? But not exactly 6, a little more than 6. Approximately 6.28. Does that number look vaguely familiar? Think back to your junior high days.
2 times pi.
2 times pi. It takes exactly 2 pi radians to go all the way around the circle. Because a radian is a little bit smaller than a 60-degree angle. So a degree is very small, right? A radian is much larger. A radian is almost 60 degrees. In fact, if you write this down, a radian, we'll abbreviate RAD, is approximately 57.3 degrees. Approximately 57.3 degrees. Some other thoughts then on this topic. We know that 1 revolution, right, meaning a complete turn, that's a revolution, right? 1 revolution is going to be equal to 360 degrees, right? That's a complete turn, is a 360, okay? And that's going to be equal to 2 pi radians. So a complete turn, 360 degrees, or 2 pi radians. And if that's true, if we lock in just on this right here, then if we divided both sides by 2, we could say that pi radians equals 180 degrees. And this is a fact that we're going to use a lot. The fact that pi and 180 degrees are exactly the same thing. Now, you might remember, by the way, your formula for the circumference of a circle, 2 pi r, 2 pi radians times the length of the radius, because that's right here. 2 pi of these radius lengths come around here, and then there's that's 6, and then there's a little extra finish out, 6.28, blah, blah, blah. Okay, so that's kind of where that whole thing comes from. Questions on this? So, we're used to degrees, what if we needed to convert to radians? Next thing in your notes, converting degrees to radians. Converting degrees to radians. To convert from degrees, which I'll abbreviate DEG, to radians, which I'll abbreviate RAD, you simply multiply by pi over 180 degrees. Think back to dimensional analysis you've talked about in physics. Well, in dimensional analysis, the idea is multiply by fractions, right? Where the numerator and denominator are equal, right? Like 5,280 feet over a mile. Well, here we're multiplying by a fraction. Pi radians over 180 degrees because they're equal. Write this example in your notes. Suppose then we had 60 degrees and we wanted to know how many radians that was equal to. All we'd have to do is multiply class by pi over 180 degrees. So 60 degrees, and we'll put it over 1, just like in dimensional analysis, and we'll multiply that by pi over 180 degrees. Now, you'll notice that the degree symbols cancel. Remember, we wanted to cancel the units. And we'll also notice we can divide a 10 from both of these. There's something else I can cancel, though. 6 can cancel out of both 6 and 18 to get
1.
and if I multiply, I get 1 pi over 1 times 3, which is 3. We can leave it as an exact value, pi over 3 radians. Think about it. If pi is 180 degrees, a third of pi would be 60 degrees. 60 degrees is pi thirds radians, or pi over 3 radians. By the way, if you want to jot this in your notes, radians are technically unitless. So we don't typically write radians. Typically, we would leave it as, what is 60 degrees? It's pi over 3. The problem is we're so used to everything having units, right? Feet, inches, degrees, whatever. So to help you, we will allow you, I say we, I'm schizophrenic now. I will allow you to write rad, as your unit if it just really bothers you to not say a unit, but technically, radians are unitless, which is going to be very valuable in physics later in the year. But 60 degrees is pi over 3. Write this one down. 330 degrees is how many radians? Again, radians doesn't have to be used there, but to help us ourselves wrap our brains around it. 330 degrees, what do we have to do, class?
Multiply by pi over
Multiply by pi over 180. So put the 330 over 1, multiply by pi over 180 degrees. Let's cancel away the degrees and the 10 and 3 again to get
11 and 6.
so 11 pi over 6. And oftentimes radians are expressed in this fractional form that includes a fractional part of pi. Okay? You get the idea. We're going to be doing a lot with pi this year. This is why seniors get to celebrate Pi Day, because you're going to have a whole lot to do with pi. Last year, nothing. Year before, nothing. Year before, nothing. Why would you celebrate Pi Day? You didn't use pi. By the time we get to Pi Day this year, you're going to feel like you've earned that pie that you are eating. How about 72 degrees? Go 72 degrees and convert that into radians. How do I go from degrees to radians, class? Pi over 180. Cancel away the degrees. Ooh, I can't cancel off zeros this time. What can I cancel?
2, 18, 3.
I can actually cancel an 18 if you happen to know your 18 times tables.
Yeah, well, I know.
I see 9, right? I see 9, because I can divide 72 by 9 easily enough.
8.
8. Remember times tables. And the 180 I can divide by 9, okay.
20.
20. Ooh, I can still divide more. Yeah, even better than that. 4. Take a 4 out to get
2
and 5.
2 and 5, and we can get 2 pi over 5. Now here's the good news. Ethan's over there like, man, I don't remember my division tables and all that stuff. Your calculator can do it for you. If you'll enter the 72 over 180 as a fraction. So on your calculator, type in 72 fraction 180, and then enter, and it'll reduce it to the 2/5. You just have to remember to put pi back in the answer. And I'm always thinking of pi, so I don't forget. All right, how do you fractions on your calculator? Oh, there's your fraction. No, that's a negative sign. There's your fraction bar right there. So 72 fraction 180 equals, and there it reduces it. Boom. So, if you're just really bad with your divisibility, now in some, like this one here, I can do that in my head.
Yeah.
It's faster to do that in my head than on the calculator. That one, because I'm knocking off zero, I can probably do that faster than pulling out the calculator. Maybe that one I want the calculator for. Does that make sense? Questions on this? I want you to do 1 through 11, the odd, on page 39. 1 through 11, the odd, on page 139. Converting degrees into radians. Let's go and take a look at these odd problems together. Number 1, 90 degrees. How many radians? Quentin? Pi over 2. Number 3, negative 30 degrees. Jamie?
I have pi over 6, but I forgot about the negative.
So?
Negative pi over 6?
Negative pi over 6.
Okay.
Number 5, Ethan?
3 pi over 4.
3 pi over 4. We can say 3/4 of a pi, if you will. Number 7, Quentin?
5 pi over 8.
5 pi over 8. 5/8 of a pi.
You go over that one eventually.
Yeah.
Yeah, let's do it after we get the other answers. 720 degrees, Ethan.
4 pi.
4 pi. And number 11, of course, we already did this one as an example, Jamie, but
Pi over 3.
pi over 3. Let's take a look at number 7. We've got a 112.5 degrees times pi over 180. I don't know that our calculators can put a decimal into a fraction. And I think that's the problem we ran into, right? We tried to put, there's my calculator, tried to put 112.5 fraction 180, and the calculator can't do that. So you know what you can do is go ahead and do the division. Do 112.5 divided by 180, and it gives you a decimal. Go and do that. And then you can convert, if you don't remember your fraction decimal equivalents from days gone by, your junior high days, 0.625. If you don't remember that's 5/8, the bottom of the calculator, you can change fraction to decimal. Second function, f to d. And there's your 5/8, and you stick the pi in there. Does that make sense? Now, Quentin, how did you figure it out?
Exactly like that.
Exactly like that. Great job. All right, Jamie, does that make sense now? No, it does not make sense. No, not fraction, divided by. So 112.5 divided by 180 equals, there's your decimal, then second function, fraction to decimal, and there's your 5/8. And you were able to get yours just with division. And it was able to put it in a fraction form, or did you have to tell it to
Well,
change
I
it to
had
fraction?
shed S to D.
There you go, and there's your fraction to decimal. Perfect. All right. All right, questions on that? All right, next thing in your notes. Degrees into, or radians into degrees. Converting radians into degrees. Sometimes we'll get answers in radians, and frankly, that's just not how our brain ticks, right? Like, we think degrees. We've thought degrees since 4th grade when angles and protractors were first introduced to us. So for our practical thinking, being able to convert radians to degrees is a very good thing. Well, you realize this is the opposite operation, right? So it's not too hard to figure out that you multiply it by 180 degrees over pi. Multiply by 180 degrees over pi. You're going to do the exact opposite. Multiply by the reciprocal. Now, how can you, that's exactly what I was about to say. The problem is students get mixed up. Which way do I go? Think about it this way. Go back to that initial example, 60 degrees, right? If you put it over 1, I need degrees to cancel with degrees. So I've got to put 180 degrees on the bottom so degrees would cancel, right? And of course that means the pi has to go on top. Write this example in your notes, 5 pi over 4. Well, here, what do I need to cancel out? The pi. So it stands to reason then that the pi has to go on the bottom, leaving the 180 degrees on the top. Also, I don't have any degrees in here. To end up with degrees, I need degrees in the top. So if you think the way we did for dimensional analysis, what do you need to cancel? Set it up that way. It shouldn't confuse you. Does that make sense? Just think, what's canceling? To get radians, I need degrees to cancel out, and I need pi. Here, I need pi to cancel out, and I need the degrees. And so here, I just do it on the calculator. 5 times 180 divided by 4. 225 degrees.
Simple enough.
Yeah. How about this one? 7 pi over 10 equals how many degrees? What do I need to do to convert these radians, class, into degrees?
180 over pi.
Multiply by 180 degrees over pi. And again, if you think of writing those degrees, that'll help you to think, okay, I need the degrees up here. And of course, we need, class, the pi to cancel. I can also, though, cancel 10 and 180 to get
118.
118?
1 and 18.
Oh, 1 and 18. There we go. 1 and 18. So 7 times 18 degrees, 126 degrees. And I can convert my radians into degrees that way. Sometimes it works out just downright obnoxiously, though. 3 pi over 11 equals how many degrees? Well, of course, class, we need to multiply by 180 over pi. The pi's are going to cancel. And nothing really else is going to cancel, so we're going to have to multiply 3 times 180 and then divide out the 11. And,
49.091 degrees now.
yeah, it just keeps on going, right? 49.09, blah, blah, blah. For our purposes, we'll just round to the nearest tenth. 49.1 degrees, we might say. Though technically we can't say equals that, but it's approximately equal to that. Okay, because of the pi value that's automatically factored in, it's kind of gnarly. In fact, if we had 1 equals how many degrees? Well, if you're trying to equate something to degrees, it must mean radians. And again, you won't necessarily see rad because technically radians have no unit at all. You would just see 1. Guess what we still have to multiply by?
180 over pi.
But there's no pi to cancel, is there? So you're literally going to multiply times 180 divided by and hit the pi button on your calculator. Go ahead and do that. 57.295, blah, blah, blah. Again, let's round to the nearest tenth and we get,
57.3.
oh yeah, 57.3 degrees. What I told you a radian was going to be, right? That's also got 3 sig figs in it, by the way, if we're thinking 3 sig figs. But again, approximately 57.3. So what if we had a 2.67 radians is how many degrees? 2.67 radians is how many degrees? And again, there's no pi to cancel, so we do multiply by the 180, but we have to actually divide out the pi. And of course it'll give you an irrational value, but we'll round to the nearest tenth.
153.
Or perhaps to 3 sig figs, since there are sig figs to go off of. Still 153, it's just with or without the point 0. Okay, questions on that? Another way to think of this, does this make sense? Well, remember, if pi is 180, 180 degrees is 3.14. This is a little less than 3.14, right? So we should get something that's a little less than 180 degrees. That makes sense, okay? Practically. Questions on these? I want you to do 13 to 19, the odd now. 13 through 19, the odd. And for these, because they factored a pi in, you do not need to use the pi key. You'll cancel the pi's. Notice also they want 4 sig figs in your answers. 4 sig figs in your answers. And I'm going to say that's just if it doesn't work out evenly. If it works out evenly, let's just be lazy. Yeah, we'll race later. Speaking of lazy. All right, let's take a look at our answers. Number 13, what did you get for the equivalent of pi over 3, Ethan?
60 degrees.
A third of a pi would be 60 degrees, since pi is 180. Number 15, what did you get for a fourth of a pi? Jamie?
45 degrees.
45 degrees. For number 17, what did you get for a sixth of a pi? Quentin?
30 degrees.
30 degrees. And then number 19 is the weird one, right? 3/7 of a pi. Ethan?
77.14 degrees.
Good. Here's where we got to go 4 sig figs, as they said, 77.14 degrees. So we get all 4 of those correct. Okay, questions at all? All right, next thing I want you to get down in your notes, a couple of really one more important angle, and that is that if pi is 180, then 90 degrees is exactly half of a pi. 90 degrees would be exactly half of a pi. And this is going to be important because, after all, geometry concept here, but it kind of bleeds over into trigonometry as well. When you talk about 90, that's special because if 2 angles add up to 90, class, we call them complementary angles. Well, in terms of radians, if 2 angles add up to half a pi, they are complementary angles. And if 2 angles add up to pi, they would be supplementary. So next thing in your notes, finding a complement. Finding a complement. And again, complement, not complement. That would be, don't you like my tie, class? Don't I look very nice today? And then you would say, yes, Mr. Nadasky, you look very nice today, sir.
Sir.
And give your very dutiful response so that you can graduate at the end of the year. That would be finding a compliment. Finding a compliment, you simply would subtract 90 minus the angle. But not 90, pi over 2 minus the angle. Similarly, to find a supplement, you subtract not 180 minus the angle, but pi minus the angle. So to find the complement of an angle, pi over 2 minus the angle. To find the supplement, pi minus the angle. So for instance, if I gave you an angle of pi over 6, and I said, well, what is the complement of pi over 6? To find the complement, class, we subtract
half pi of the angle minus
half of a pi minus the angle. So we'd say pi over 2 minus that. And of course, we could get our common denominator. So instead of 1/2 of a pi, we could make this 3/6 of a pi, right? 3 pi over 6. Multiply top and bottom by a 3, right? So 1 pi over 2 becomes 3 pi over 6. And now we subtract 3 pi over 6 minus 1 pi over 6 gives us 2 pi over 6. That's the complement. Or we could reduce that down, pi over 3. That's the complement of pi over 6. Easy enough? What if we wanted to find the supplement? We wouldn't subtract from pi over 2, we would subtract from pi over 1, technically. You still need a common denominator, don't you? So instead of pi over 1, multiply top and bottom by, and make this 6/6 of a pi, right? Still a whole pi. 6 pi over 6 minus 1 pi over 6 gives us
5 pi.
So the supplement of pi over 6 is 5 pi over 6. Easy enough on how to find complement and supplement. You're not subtracting from 90 degrees and 180 degrees anymore. It's pi over 2 and pi. What if our angle was 3 pi over 8? Let's go with an angle of 3 pi over 8. And we want to find the complement and the supplement. To find a complement, class, we have to subtract from pi over 2. Not 90 degrees anymore, pi over 2. So instead of writing pi over 2, how might I rewrite this?
4 pi over 8.
Multiply top and bottom by 4 to get the common denominator. 4 pi over 8. Now we can subtract.
1 pi over 8.
Pi over 8. But if we wanted to find the supplement, we wouldn't subtract from pi over 2, class. We'd subtract from pi or
8 pi over 8.
8 pi over 8, which would give us a supplement of
5
5 pi over 8. Questions?
Nope.
Still seem pretty easy. Okay, so let's suppose instead of 3 pi over 8, let's suppose our angle was 0.58 radians. How do we find the complement? Calculator. You're still going to take pi over 2 minus, but on your calculator, you're going to take pi divided by 2 equals, get that value, and then subtract 0.58. And since this has 2 sig figs, we're going to go 2 sig figs.
0.99.
Correction. This is 2 decimal places. This is subtraction, so it's place value. So we're going to go 2 decimal places.
0.99.
0.99. Did y'all get the same thing? 0.99. What if we wanted to find the, make sure Ethan's got it, pi divided by 2, and then subtract the 5.8? Okay, clear. Okay, so where's the pi button? Oh, you're kidding. You're doing the second function of pi. That's awful. Divided by 2 minus 0.58. That's it. All right. What if we wanted to find a supplement, class? We don't subtract from pi over 2. We subtract from pi. So literally on your calculator, pi minus 0.58. And again, since it's subtraction, we're rounding to place value, so 2 decimal places.
2.56.
2.56. Someone else verify?
Yep.
Questions on this? All right, I want you to do page 40 now, 21 to 31, the odd. Page 40, numbers 21 to 31, the odd. 21 to 31, the odd. 21, 23, 25, finding the complement. 27, 29, 31, finding the supplement. Let's go and take a look at these together. Number 21, what is the complement of pi over 3? Ethan?
What is the complement of, oh, I didn't. I
Number
got
21?
confused. I got confused.
Okay, so how do we find the complement?
You minus pi over 2.
Right, pi over 2 minus whatever angle. In this case, it's pi over 3. And we get a common denominator. What's the common denominator between 2 and 3?
6.
6. So we multiply top and bottom by
3.
to get 3 pi over 6, and we multiply top and bottom by
Okay, to
2 to get 2 pi over 6, and so 3 pi minus 2 pi all over 6,
pi over 6.
that's your complement. Does that make sense now?
Yeah, it does.
All right.
So I was confused.
What about number 23? What's the complement of pi over 12, Jamie?
5 pi over 12.
5 pi over 12. How about number 25, the complement of 1? Quentin?
0.57.
0.57. Number 27, the supplement of 7 pi over 8, Ethan.
27. I never got that far. I
Okay.
was trying to figure out.
So how do we find a supplement?
Pi minus from pi.
Subtract from pi. And again, let's get a common denominator by rewriting the 1 as
8.
over
8.
8/8, right? And now we can subtract him and get
Pi over 8.
pi over 8. Number 29, the supplement of 5 pi over 12, Jamie.
I did it wrong. I have 1.83.
Oh, yeah, we don't want that. Because if we've got pi in the answer, let's go and just subtract from pi by rewriting pi as a fraction.
12 12.
12 12s. And we subtract him and get
7 12. 7 pi over 12.
7 pi over 12. How about number 31, Quentin?
0.83.
0.83 for our answer. Questions on that? A little bit of trouble there. We'll go over
No, I'm
more of
good
this
now.
tomorrow.
I'm good now.
All right, no homework this evening, and we'll review over this more tomorrow. Have a wonderful rest of your day.